Hi, my name is Rob Mucha, and this is my final project for Engineering 307, Ocean Wave Energy Conversion. And the topic I covered today was tidal hydrokinetic energy. What causes the tides? Several factors cause tidal variations on the Earth. The main factors are the moon and the sun's gravitational pull on the oceans and the centrifugal forces of the Coriolis effect of the Earth's rotation. According to Newton's law of universal gravitation, the gravitational attraction between two bodies is directly proportional to their masses and inversely proportional to the square of the distance between the bodies. The moon, therefore, exerts twice as much tide-generating force than the sun due to the distance relationship to the Earth. The sun and the moon's gravitational forces create two bulges over the ocean. This elevation change in seawater, in conjunction with the rotation of the Earth, creates tidal variations around the world. Since bodies of land are irregularly spread over the Earth, we experience three different types of tide variations, which are observed on the bottom right. We have semi-diurnal tides, and mixed diurnal tides, and their distribution around the world. But we'll talk about that in the next slide. Shorelines of continents also play a strong influence on the magnitude and strength of tides and magnify their effects. If you look at the figure at the top right, we see the Bay of Fundy in Nova Scotia, Canada. The Bay of Fundy is a funnel-shaped bay which is known to experience tidal changes of 15 meters, which is the highest in the world. Its unique geography creates an amazing variation of tides. You can observe this bay in the top right corner where we have at the choke point on Minas Pass. This is where they observe the largest tidal variations. In the top left corner, we have a diagram of the moon and the sun's relationship to the Earth and its tides. The largest tides are called spring tides, and they occur when the sun and the moon are lined up and exerting their gravitation force on the world's oceans. And those are called spring tides, and this is where we see our largest tidal variations. Neap tides occur when the moon and the Earth are at 90-degree angles from one another, and this 90-degree angle opposition creates lesser tides that we see on the Earth. Tidal spectra and sea oscillations. The large graphic on the left is amphidromic points on the Earth and shows regions where the largest tidal variations occur. The areas in red see at least 1 meter of tidal elevation change, and the areas in dark blue are amphidromic points or nodes with no tidal variation. In terms of a standing wave, and we can see that diagram on the bottom right, the node is the part of the wave where there is zero amplitude change, where the antinode, or where you would see the maximum amplitude, positive or negative. This map also shows the scale of the tides and depicts possible areas where we can employ tidal energy. You can see various regions where there would be wise to explore the potential of tidal energy. In specific, the Pacific Northwest of the continental United States and also Alaska show great potential for tidal energy due to the large variation of tides and the many islands that create ideal bathymetry suited for tidal energy conversion. The vertical motion of the tides near the shore cause the horizontal movement of the water, and this water movement creates the currents, and these currents are the focus of this project as well as the energy conversion devices. On the top right hand corner you can see the tidal phases. We have a diurnal tide, and that consists of one high and one low tide each day. The semi-diurnal tides are 2 high tides and 2 low tides each day. And then the mixed tide is 2 high tides and 2 low tides, and each tide change are of different heights. Types of tidal energy conversion. There are 4 types I'm going to discuss in the next 2 slides. The 2 that are primarily used in today's technologies is the tidal barrage and the tidal turbine. The other 2 are in the R&D or conceptual phase, and there's no commissioned projects at this time, but I think it's relevant to discuss these because they can be the future of tidal energy conversion. Tidal barrages operate similar to hydroelectric dams. Barrages are installed at an inlet of a tidal basin or lagoon. Sluice gates control the water levels and flow and allows the tidal basin to fill on an incoming tide. Once slack tide has arrived, the sluice gates are closed and the potential energy is stored in the basin. Once low tide is reached, the water is released back into the ocean in a controlled fashion and spins turbines that generates electricity. There is also multi-directional or two-way turbines that can generate electricity on an incoming tide and an outgoing tide. These systems take advantage of the potential energy and difference in height and gravity's effects and water's ability to find its level. In the top left corner, you can see the illustration very clearly where we have the barrage, which is the wall or like a dam structure, and then you see the tidal basins at a different potential than the ocean, and water is finding its level and it's pushing a turbine and generating electricity. The second common technology currently deployed is tidal turbines. They are very similar to wind turbines, and they're placed on the seafloor where there is strong tidal flow. Tidal turbines are fixed to the seabed either by a gravity-based system or drilled pylons. They are very much like underwater windmills. Although they have to be more robust and sturdier and much heavier than wind turbines due to the conditions that they face in the oceans with rough seas, waves, and the corrosive aspects of seawater. Since water is 832 times denser than air, tidal turbines have the ability to be much smaller in rotor size compared to their wind cousins. These turbines also have the ability to alter their active pitch and yaw of their blade to enhance efficiency during different current speeds. Turbines are also connected to the grid with undersea power cables, and typically they have an operational life of about 25 years, and then there's a 5-year maintenance cycle. And you can see an illustration of a tidal turbine on the right side. And then finally, on this slide, we have a tidal fence, and this is also a turbine, and they can be deployed horizontally or vertically, and these arrays also capture the energy by rotating these blades, and it generates electricity at the hub or the access point. And the fourth type of tidal energy conversion is dynamic tidal power. As you can see from the illustrations on this slide, this is a very large structure that is designed to impede the tidal flow running parallel to a coastline. This potential height difference allows for turbines to spin much like the tidal barrage that was discussed in the previous slide. Dynamic tidal power generation remains in developmental stages and is based on data and models of known tidal behavior in certain regions. Scientists and engineers are very confident with these theoretical predictions, which makes this a viable option in the near future. Dynamic tidal power dams are very large, and they run usually 30 to 60 kilometers long and run relatively straight out into the ocean. These dams have to be designed this way by necessity, and they're much larger than any current coastal structures, which would make them extremely expensive to build. Hence, none has been currently done. However, these structures have the ability to be used for multi-purpose functions, which makes them maybe a little bit more redeemable as a form of tidal energy conversion. Their functions could be a land reclamation project, a bridge between islands, and also provide mainland coastal protection from like very treacherous seas. Some of the advantages of this type of system is that they do not require huge tidal ranges in order to operate, which is a very advantageous thing since most tidal energy technologies are very site specific. These can be deployed just about anywhere that's on the ocean. Although there is some significant drawbacks, as these are very large and expensive projects, and they would also cause certain ecological transformations to the land that could impede migration paths and alter sea life and be a detriment to an area. So further studies needs to be done on the impact of such a station. Conditions for tidal energy. Now, it is deemed economically suitable if you can find current velocities of 1.1 meters per second. Now, ideal velocities in those locations should also exceed 2 to 2.5 meters per second during spring peak tidal currents. Also, you're looking for areas that have relative depths between 20 and 50 meters. Now, areas with tidal current fields that reverse along a defined axial direction is ideal because engineering problems occur when there is a lot of variation in those currents, and directing your turbine at certain times would be a definite challenge. Also, seabed composition of a solid fixed bottom is ideal. On the left-hand side, we have a hydrodynamic study of San Marco Bay in Brazil. This is a possible tidal project and currently in a feasibility study for possible tidal power generation. There are 3 sites on the map that show velocities that are greater than 1.1 meters per second on a 31-day period. The 3 zones are identified as promising, referred to as zones A, B, and C. For zone A, only the area located outside the waterway that gives access to port facilities has been considered. This zone has the tidal currents with velocities higher than 1.1 meters per second 55 to 60% of the time, and it lies in about 25 to 40 meters of depth. Zone B, with a uniform depth of 22 meters, has the highest percentage of the 3 zones, with current velocities peaking about 60 to 65% of the time. However, this location is inconvenient because this is a navigation channel. Finally, Zone C has the largest velocity, sorry, not the largest, but the lowest velocity, and the occurrence is about 50 to 55% of the time, and the water depths range from 30 to 35 meters. Other areas close to the above identified zones, as well as spots in the southern half of the bay, have been discarded due to low water depths of less than 20 meters. Now, site selection for tidal stream devices depends on the available power and the site characteristics and the possible environmental and socio-economic impacts. For future research efforts need to be taken into consideration for conflicting use of marine environments such as fishing, shipping, offshore, wind habitation protection, and other technical limitations. Tidal energy sites around the world have been developed. Perhaps the largest is Shiwa Lake Tidal Power in South Korea, which is shown in the image in the top left. This was a very large-scale tidal power plant, in fact the world's largest, generating about 254 megawatts. Shiwa Lake was an artificial lake constructed by the South Korean government, and its size was about 43.8 square kilometers. This was done by creating a seawall about 12.7 kilometers that enclosed Gyeonggi Bay. Initially, this project was used to obtain fresh water from seawater, and also had other purposes like land reclamation and coastal protection. Once the water quality conditions deteriorated due to the tidal mitigation, the government searched for other solutions for this wall. One of the solutions that was proposed was to create a tidal power facility. Shiwa generates about 552 gigawatt hours, which is the equivalent of 86,200 barrels of oil. Shiwa tidal power generates one-way power twice a day at high tide. The sluice gates are closed, and as the tide comes in, it isolates the reservoir at its lowest level. Then the gates are opened and the 10 turbines operate. This electrical power is able to satisfy the needs of a population of about 500,000 people annually. The next power plant is the Lawrence tidal power, and it is shown on the bottom left, and its power generation capabilities is 240 megawatts. This happens to be the oldest tidal power plant in operation and was opened in 1966. This tidal power plant is situated on the Rance River in Brittany, France. This is a 145-meter long obstruction and contains about 24 reversible bulb turbines rated at about 10 megawatts each. The average tidal range in this area is about 8.2 meters, and this power project serves about 130,000 households every year. Now, the Maijin tidal power, which is in the top right hand corner, is situated in Scotland. This happens to be the world's biggest underwater turbine under development. This will provide about 175,000 homes with power. It currently uses 4 1.5 megawatt turbines. The second phase of this project should reach a capacity of about 398 megawatts, and this is predicted by 2020. These turbines are massive. Each rotor is about 18 meters in diameter. The turbine is going to be situated in the inner sound of the Pentland near Caithness, Scotland, where current speeds reach up to about 5 meters per second. And then lastly, the Annapolis Royal Generation, which is in Canada, which is on the bottom right hand side. This is located in a sub-basin in the Bay of Fundy, which is an area which experiences extreme tidal flows. It currently generates about 50 gigawatt hours and powers about 4,000 homes. Was initially designed to be a transportation link, so this had a dual purpose. It also mitigated flood problems. The plant has a single 4-blade turbine, and sluice gates are closed on the incoming tide and then opened on a high tide. So engineering challenges we see with the tidal barrage form of tidal current conversion. These are large man-made structures, dam-like structures that ultimately change the movement of water because man is manipulating the flows of water into these estuary and basins. So this affects the wildlife that lives in this area drastically because we are manipulating the water flows and the natural processes in the area. So the disruption of natural habitat is a large concern. Increases in sediment buildup and turbidity. This creates water quality issues and may prohibit certain types of natural wildlife from using the area, and this might have effect on fisheries and local resources that people in that area rely on. There also is, recreational navigational issues. When we build a large wall structure, vessels will have a very difficult time traversing through that area. It's not impossible. There is lock systems in some of these structures, but ultimately it's not the free flow. And tidal barrages are very costly to build, and they require heavy machinery and equipment in the area to build, decommission, and maintain. So this creates a lot of disruption in the area as well. And tidal barrages also are very site specific. You can't build these everywhere. Well, you can build these everywhere, but they require lots of money because you would essentially need to build a basin for this tidal water to be caught in. So these are some of the hurdles that engineers face with tidal barrages. With tidal turbines, obviously these structures have blades and have the ability to impact wildlife that travels through the area. They also, the generation of electricity is right there, so the acoustic and electromagnetic disturbances in the water, to understand what kind of marine life live in that area that might be disturbed by that. It also alters the natural tidal movement of water and the rise of the tides. Essentially, we are taking energy away from this current, so there is an ecological impact involved with these blades removing the natural flow. And these blades are massive. Some of these are like 18-meter long, and certain vessels would not be able to traverse over them without damaging these. So they can cause navigational issues in channels, and these turbines are also much more delicate and prone to damage with big waves that you might see out in the open ocean and rough water. Regulatory agencies. On this slide is a list of regulatory agencies that would most likely be involved in most tidal energy projects. Probably the biggest hurdle for most tidal energy projects is the government regulation and permitting. There's a plethora of statutes and regulations relevant to the oceans, coasts, and the management of marine resources. While there's over 40 principal statutes on the federal level, only a handful is directly relevant to tidal power jurisdictions. There's a large web of agencies that would need to be involved in a tidal project, and I will highlight a few of the key players. But the regulatory framework is much larger and a very confusing mess. The primary federal agencies for ocean tidal jurisdiction include NOAA, which focuses on conservation and management of the nation's coastal and marine resources. NOAA is the only agency that has licensing authority and regulations specifically designed for marine renewable projects. NOAA is also involved in tidal projects if the tidal project is located within protected areas and marine sanctuaries. The Mineral Management Service administers its authority under the Outer Continental Shelf Lands Act and the Energy Policy Act. It grants the MMSS a new authority for federal offshore alternative energy uses and regulates alternative energy uses, including wind, wave, and solar energy. FERC. FERC is an authority that comes into the Federal Powers Act and is an independent agency regulating interstate transmission of natural gas, oil, electricity, and hydropower projects. FERC also has regulatory authority over terms and rates for power supply contracts from the wave power projects to the local utility. FERC issues licenses for private hydropower development on navigable waterways, federal lands, and Commerce Clause waterways. It includes consulting with a wide range of stakeholders. Tidal electric power sold onto the grid is another jurisdictional area of FERC, identifying environmental issues through scoping process and preparing environmental documents such as the environmental assessment or the environmental impact statement licenses that are issued by the Commission. The traditional licensing processing through FERC takes several years to complete, and the license is issued for 30 to 50 years. As you can see, that the regulatory processes are extremely complicated. Just from the few of the agencies I've listed, it gets even more complex with the various state and local agencies that get involved. This is probably one of the most prohibiting factors to why tidal energy isn't a mainstream form of electrical production in the U.S. Framework for success. The forefront of renewable energy industry has been Europe, and the government bodies of the EU have made significant commitments in order to achieve a 20% renewable energy share on the continent by 2020, and plan to continually increase this share as time goes on, with a target of 27% by 2030. Some of the mechanisms that the EU deploys to meet their targets are feed-in tariffs, loan guarantees, soft loans, investment grants, and tax incentives. Policy mechanisms designed to accelerate the investment of renewable technologies in the area. And it achieves this by offering long-term contracts to renewable energy producers, typically based on the cost of the generation of each technology. The tidal energy industry needs government partners while the technology is new and the risks deter private sector investment. Federal governments will need to support the industry more in the early stages and less as the industry learns to become competitive with other renewable energies. The goal of feed-in tariffs is to offer cost-based compensation to renewable energy producers, providing price certainty and long-term contracts that help finance renewable energy investments. Loan guarantees are a promise by one party to assume the debt obligation of the borrower if the borrower defaults. Soft loans are loans with no interest or below market interest, and they also provide concessions to the borrower like long repayment periods. These loans are usually provided by governments for projects that they deem worthwhile. Investment grants is an amount of money given to the private sector developer by a government so they can buy the necessary equipment and infrastructure to improve the quality of life of the citizens in the local areas. They are also available to support the development of renewable energy. Tax incentives are also given by government to encourage business to spend more money by reducing their tax burden for the projects that they're creating. In-stream tidal technology is ready for pilot-scale demonstration in the U.S. Experimental prototypes have been operating around the world for years. Although we're technologically ready for demonstration, many important questions about the application of in-stream tidal energy generation remain. What type of size and array would yield optimal economics? What device types and tidal technology is optimal for a given site? What will the environmental and ecological impacts be? Can government subsidies and tax incentives cultivate the tidal energy industry? Hopefully some of these questions were answered by this project. I can say that from what I've researched, that we're on the way to seeing a lot more of these tidal projects being coming from conception to reality within the next few decades. There is a great promise in this energy because there's so much of it available to us and coasts around the world. It just requires investment from governments to get the ball rolling, so the private sector would be on board. Thank you for listening to my presentation. I've included my notes and resources in a Word document that will be submitted with this video. Thank you very much.